So before I get into how induction works, I should first preface this by explaining a little bit here that induction is a fairly different flavor of process than the sort of things we've gotten so far in this semester. I wouldn't say that everything we've seen here has been, strictly speaking, applied. We have seen a lot of things that are fairly conceptual, at the very least, in terms of how we've looked at them, but everything we've seen does have very much a set of real-world contexts in which we can place them, and not to say that you can't do real-world examples of induction or that you can't use inductive reasoning in a real-world setting, but what we're doing here is inherently meant to be more abstract, where what we're doing is more of a proof-based process. We saw some proofs in Chapter 5, and you've probably seen things with no-show tables earlier on in geometry in high school or middle school, whenever you took it. But this, it's kind of a horse of a different color, as it were, because it's more of a rigorous proof method than probably anything you've seen before, and even in itself, it's not the most obvious process. I remember the first time I looked at induction, the first time I had a class that used induction, I ended up throwing the book across the room at least once because it's very frustrating, or at least it can be very frustrating to see it the first couple of times because it really can feel like a poorly explained magic trick when you see the process here, especially early on. So it's really important here that you take your time working your way through here and that you understand that this is not simple, obvious stuff for most people. We're not going to go into as much detail as you possibly can with induction, but I would consider this to be one of the harder sections that we get all semester. Whether or not that proves to be the case for you is a different matter, but just know that this is a little different. Anyway, to understand the idea for induction, we're going to think of it in a very, I wouldn't say classical sense, but it's the standard example that you get when you think about induction, where, just to get some context, inductive reasoning as a general process is the idea of taking specific examples and building them out to draw a general conclusion. There's no guarantee that there's good logic there in terms of something like inductive reasoning, where you could say that because in Florida we're known for having all those weird crimes that people see, like the guy who tried to rob a drive-through with an alligator, or the person at the pet store who slapped someone with a leopard gecko. You might see those and you think that everyone in Florida is therefore strange and criminal, basing your general conclusion on those specific examples. That would be inductive reasoning. But just because we have those nice cases and we can think about those general conclusions doesn't mean they're necessarily very good, but it's at least worthwhile to think about what that idea is as we're getting into here. But anyway, I got a little distracted. But for this, what we can think about is something like climbing a set of stairs. So let's say you get up to a staircase and you're in the library or something, and you think about it. Well, you look at that first step, you can get onto that first step, right? You can step up onto that first one. That's good. And then thinking from that first step, if you're at any other step, and it can be the first one too, it's not as interesting if it is, but if you're on some other step, and presuming that these steps are all the same length and width and height, they're all very consistent, if you can go from that step one more up, whatever the next one up is, then presumably, because you could get onto that first step, and you could take any other step, you could keep climbing the stairs indefinitely, as long as they stayed consistent. Now, this is a bit ableist at the outset. Stairs are kind of the enemy of wheels in some sense, but beyond that, human beings don't have infinite stamina for going up staircases. Otherwise, stairmasters wouldn't be high-priced gym items, now would they? But we can apply that same sort of logic to thinking about arguing for the truth of certain mathematical processes. In particular, we can think about this for seeing things in terms of natural numbers and integers, where this is the idea of mathematical induction, where mathematical induction exists in two steps. We start by saying, at the first case, whether that's at n equals 1, n equals 0, n equals any number, we say, does the idea we're expecting hold? Well, this is what's called the base case. It's what we're starting from. It's being able to get onto that first step of the staircase. And then the other step that we need here is to just show that if we can be on one step, then we can get to the next. This is what's called the inductive step, as it were, where in more exacting notation, we say something like if sk is true, if the kth step in our process is true, then we use that to show that the k plus first step is true. And if we have both of those things, then we can argue that the pattern holds forever. Because the nice thing about numbers is that unlike people, they don't tend to get tired climbing upstairs. They can just keep going and going and going for as long as we need them to. And we'll get to some ideas in terms of how we can actually prove things this way, but at least to start, the next thing we're going to look at is just setting up the notation for things like these base cases and inductive steps in a proof by mathematical induction.